Good evening, everyone. So today we will be discussing on the topic that is size enlargement of the bulk particles that we were previously discussing about the conveying, storage, and other topics that as far we have covered. So today we will be discussing on very important topic on the on the basis of size enlargement. So before starting today's session, I will wait few more minutes to join people so that they can join for today's session. Okay, so we can start for today's session. So basic introduction about the topic today, that is size enlargement. So the distinguished characteristics of the size enlargement that we are talking about, it is basically we are talking about size enlargement by agglomeration process. So here what happens, they form in the process of agglomeration, they form larger entities from the particulate solids by various mechanisms like sticking the particles together by short range physical forces between the particles themselves or through the binders. The substances that adhere can be chemically or physically to the solid surfaces and form a metal bridge between the particles. Thus, the agglomerate form from the particulate solids by sticking uh, one to one each other, they form the agglomerates. So the term size enlargement, they encompasses a variety of unit operations or processing techniques which is dedicated to particle agglomeration like granulation, flocculation, extrusion. Size enlargement operations are used in material processing industry, different material processing industry with different purposes such as improving flow ability or handling ability. We have to sometimes modify our particulate solid nature, shape, size. We have to make the larger particle size because we want to make sure the flow ability of that particle through handling time or storage time, reducing some losses in the atmosphere, producing specific shapes, reducing dust issues, and improving the product uniformity and boosting their overall appearance. So basically, there are two main categories of size enlargement. One is processes that aim to control the functional properties such as granulation, and the processes that target the production of the defined forms such as tablets or pellets. So, in order to control or change the functional properties of the solid, that is, by the process of granulation, we apply some size enlargement processes such as tumbling agglomeration or different kind of tumbling agglomeration process are there. Either other processes are like fluidized agglomeration or um, any kind of mixed agglomeration. There are different kind of granulation process are there. The defined forms of the product is maintained by size enlargement process, which is known as pressure agglomeration. This pressure agglomeration or compaction agglomeration is is basically a dry granulation process. So we need to understand that what are the forces that are involved in the size enlargement operation. First one is the solid bridges that are formed. Second one is adhesion and cohesion forces and surface tension and capillary forces, and then attraction forces between two solid particles. So these are the forces involved for or responsible for size enlargement. So first we will briefly discuss about what is meant by solid bridges. So when particles come together and any kind of binding material like any dissolved solute, molten binder or chemical reaction product, any kind of binding material and the particles, when they both come together, they solidifies between them and solid bridges are formed. These solid bridges, what they do, they lock the particles together and giving the agglomerates very high strength. Just take an example like crystallization of the dissolved salt binding particles or hardening of cement or adhesive, any kind of adhesive, or cooling of molten binder in pelletization process. So these processes you can notice that the solid bridges form between the particles to particle in the presence of the binding material. They give the overall agglomerate a very high strength. Next, the force that is responsible, that is adhesion and cohesion forces. So adhesion force, that means force of attraction between different type of materials. Like suppose one binder liquid and another one is solid particle. So between them, that two different kind of materials, the force that is acting, that is adhesion force. And cohesion force is just opposite, like similar particles having when they are having attraction force, that is known as cohesion. That is particle to particle sticking, that can be considered as cohesion force. So these adhesion and cohesion forces help in the initial nucleation and growth of the granules when the powder particles stick together between themselves. You can take example like sticky kind of binders that like molasses or starch solution. They increase the adhesion between the particles during agglomeration process. So here adhesion and cohesion, both forces equally responsible to make the agglomerate product. The third force that is responsible, that one is surface tension and capillary forces. So when a liquid binder is present in very small quantity between the particles, the liquid bridges form between the particles. Now the surface tension of the liquid, they play an important role such way that they pull the particles together each other. And the capillary forces like suction in the narrow pores, they hold the particle tightly as long as the binder remains liquid form. So water in the wet granulation process of powder, they form the droplets, the water droplets, they pull or attract the particles together until drying forms and the liquid binder or water, it evaporates and ultimately they form solid bridges between the particles. And last one is different attractive forces between solid particles. Now it depends that what kind of solid particle you are handling. It may be magnetic in nature, so there will be magnetic dipole uh, interactions, or there may be different kind of the solid particles. So these are intermolecular forces like van der Waals forces or any kind of electrostatic attraction. So they are usually weak compared to solid bridges formed, but they also play important role in fine powders where the surface area is very large. So we can have the example like fine pharmaceutical powders, they stick to each other using that van der Waals forces. So we already discussed that what are the forces are responsible for making the agglomeration effective from the powdered solid material. Now the process granulation, we need to discuss in detail that how the granulation occurs, what are the mechanism, what are the kinetics, what are the different equipment, what are the different categories that belongs. So starting with granulation, the process of particle enlargement. This is done by agglomeration technique which is most significant in any kind of mechanical unit operation. So during the granulation process, what happens? Small fine or coarser particles are covered into large agglomerate, which is called as granules. So this granulation process, they transform fine powders into free flowing, dust free, and very uh, product size is also desired product size and very easy to operate. This kind of fine powders, they transform the fine powders to granules. So the aim of granulation process is to, that is most important to discuss why we are doing this operation. The aim of the granulation process is to improve the properties of the final product compared to the powder form, as they give better flow properties of the safer and cheaper transport and storage. They also lowering the cake and lump formation, especially for any kind of hygroscopic material. And they also improve the heat transfer features, obtaining a more uniform distribution of the active molecules. They also lower the power dispersion into the environment, powder dispersion into the environment. So they minimize the uh, risks or health hazard in the environment, and also uh, the handling issues are improved. Now, nevertheless, the granulation possesses numerous challenges due to the high quality requirement of the formed granules in terms of the content uniformity and physiochemical properties, such as we want to maintain some particular granule size, their bulk density, porosity, hardness, moisture content, compressibility, and altogether other things to improve the product. Like suppose you are making the drug products or making any kind of tablet, medicine or pharmaceutical industry you are working on, and at that point, if the product ultimate product quality and the shape size and any other characteristics of that drug product is needs to be maintained. So granulation, the whole granulation process is very um, mm, is very difficult to maintain the exact this kind of characteristics. So we need to maintain the parameters of that each and every processes that we are choosing, and we have to also mm, choose choose the machines or choose the equipments in such a basis that what is our requirement at the end of the product, uh, at the um, according to the end product. So uh, the we what we need, that ideal characteristics of any kind of granules should be spherical in shape, that may improve the flow, narrow particle size distribution for content uniformity and volumetric dispensing, sufficient fines to fill the void spaces between the granules for better compaction and compression characteristics, and adequate moisture and hardness to prevent breaking and any kind of dust formation during the process. So this granulation is an exemplary of particle design, and the properties of the particles acquired after granulation depend on particle size of the drug and excipients, the type and concentration and volume binder or solvents, granulation time and type of granulator drying rate, etc. This kind of all parameters play important role in the granulation process. So, the primary methods by which the agglomerated granules are formed, they include solid bridges, sintering, chemical reactions, crystallization, or deposition of the colloidal particles. So, besides another form, that is binding, can also be accomplished by adhesion and cohesive forces by utilizing high viscous binders. So generally we use the binders in a wet granulation process. So that's the point we are coming now. The granulation technique may be widely categorized into two types. One is dry granulation, another one is wet granulation. So based on the type of the method that is used to facilitate the agglomeration of the powder particles. So in dry granulation process, we use the mechanical compression or compaction to facilitate the agglomeration from the dry powder particles. So this mechanical compression can be known as slugs, and mechanical compaction we use by roller pressure. While wet granulation uses granulation liquid, that is binders or solvents, to facilitate agglomeration by forming wet mass by adhesion. So this second process, that is wet granulation, involves final step of granules stabilization by removal of the wetting phase, that is binder, to make the relevant bonds permanent. Among these two techniques, wet granulation is most widely accepted despite the fact that it involves multiple unit processes such as wet mashing or drying or screening, which is more complex and time consuming and expensive as well. But still, we follow wet granulation because it is more effective than dry granulation process. I'm extremely sorry that my internet got disconnected in between. So I'm presenting the slide again. You can refer the uh, in between lecture in the uploaded video if you miss anything. Okay, so we were discussing about wet granulation and dry granulation process. So granulation technology include roller compaction, spray drying, supercritical fluid or low high shearing mixing, fluid bed granulation, you can say extrusion. So this kind of combination of there are different categories of wet granulation and dry granulation processes. So the series of mechanism by which the granules are formed from the powder particles, they encompasses wetting and nucleation, coalescence and growth, consolidation and attrition and breakage. So these are the mechanism by which the granules are formed from the dry powdered. So classification of the granulation process based on the operating principle. First one is dry granulation, where we mainly focus on the direct physical compaction or densification process, which produces agglomerates from the dry powder. With high shear granulation, which uses rotating of high shear forces via high power unit mass with additional of liquid, that is binder liquid. And with low shearing granulation, with that uses the low shear forces machines via low power per unit mass with addition of the binder liquid. And low shear tumble granulation, which also uses the wet granulation process and rotation of the vessel or any intensifier bar by a low power unit mass with addition of the liquid. Extrusion granulation, which the pressure gradient forcing a weighted or uh, plasticide mass through a sized orifice with linear shear. They produce extrusion granulation process. And rotary granulation, where a central rotating disc, a rotating whirl and other cause centrifugal or rotational forces that spheronize, agglomerate, or densifies a weighted or non-weighted powder or extruded material, they possibly incorporating a liquid or drying. Fluid bed granulation, here the direct application of an atomized granulation liquid is happening on the solids with little or no shear while the powder is suspended by a continuous gas stream with continuous drying is happening, which is very effective. A spray dry granulation process where granulating liquid containing dissolved or suspended solids is atomized and rapidly dried under controlled gas stream, which produces dry powder. So hopefully you have learned the categories of um, different categories for the granulation processes that exist. There are other advanced categories that we are not going to cover in this class. We are going to cover only the basic categories, wet and dry granulation for this class today. Okay, so we are now going to discuss about wet granulation process. So this wet granulation employs the massing of a mixture of dry powder particles using granulating fluid, that is binder. So the significant step involves in the traditional wet granulation process are mixing of powder and ingredients, other ingredients, preparation of binder solution, mixing of binder solution with the powder mixture to form wet mass, then screening of that wet mass using any sieve, then drying of the moist granules, then screening of the dry granules through sieve for the product. The greatest disadvantage of the wet granulation is the cost associated with the process, an expensive process because of the labor, time, equipment, and space requirements, and there are a lot of materials being used in various stages of processing. Multiple processing steps add more complexity and control difficulty, heavy mixing equipment, and time consuming drying step required for the wet granulation process. Now, what are the role of binders in wet granulation? The primary role of binder is to provide the cohesiveness that is very essential for bonding the solid particles under compaction to form sagupials. Now, the binders are typically liquid in form, that may be water ethanol or isopropanol, or that can be any mixture with that, or it can be another kind of binder like molasses or any kind of other binder that can be also used for making granules. So, in a wet granulation process, the binders promote the size enlargement to produce the granules, and they improve the flowability of the blend during the process. The binder can thus improve the density and hardness of the pure by enhancing the intragranular as well as intergranular forces. The effect of wetting parameters and the jet breakup on the granule related to surface tension are significant in the kinetics of the wet drum granulation. So the growth of the pures are very sensitive to binder content, and the particle size enlargement decreased as the binder content are increased more and more. So we are now going to discuss about different stages involved in the agglomeration rate in wet granulation process. So in general, there are three fundamental sets of rate processes that determine the weight granulation behavior. One is wetting and nucleation, second stage is consolidation and growth, and third stage is breakage and attrition. So this wetting and nucleation is the initial step where the liquid binder is added on the dry powder, and they are added, and for that they cause the adhesion between the particles to obtain the distribution of small aggregates, that is they form granules in the first step, and in the second step they generally form granules and they grow, and when they grow in the second step, they also consolidate in such a way that the nuclei begin to grow as a whole in size and volume as well. For the deposition of additional number of particles onto the um, granule, and ultimately they form larger granule, and then they finally they enter into the stage of attrition and breakage, where there will be rupture of the granules with relevant formation of the relatively smaller particles due to both impact force or impact forces of the granulator, and also any kind of product handling. They break down into smaller particles. So the smaller particles are again taken for the wetting with the binder liquid, and they again form the granule, and again this cycle continues. So this picture also forms the crystal formation, the granule formation. So here what happens, the wetting and nuclei formation occurs, and they form the agglomerated nuclei. It may be immersion form or it may be distribution form. It can form like different kind of nuclei, and then they consolidate in such a way they grow by maybe in kind of layering form they may grow, or it can be colonces, they may grow as a whole. And at the third stage they will break by any kind of impact force, they will break into relatively smaller particle size. I hope this is clear to you. Um, okay, so in the Slomochowski theory of agglomeration, two different modes of agglomerations were defined. One is perikinetic and another one is orthokinetic processes. So there is fundamental mechanistic difference between these two processes, perikinetic and orthokinetic, for the agglomeration mechanism. So this classical theory explains that how suspended particles they collide and stick together to form larger clusters. The key idea is the rate of agglomeration depends on how frequently the particles collide and how many of this collision lead to sticking. So first one we are going to discuss about perikinetic agglomeration process. So, perikinetic agglomeration, where the rate of aggregation is in general determined by the frequency of collision and the probability of cohesion during the collision. If the collisions are caused by only the Brownian motion or the random movement of the particle in the mixture, the process is called perikinetic aggregation, and it is solely driven by the diffusion process. It is unaffected by any kind of fluid mechanical condition. So here the smaller particles in colloidal suspension continuously undergo different Brownian motion. These particles collide with each other and stick together due to the attractive forces between them, and multiple collisions can lead to formation of the multiple multi-layer or multi-particle aggregates. This Brownian diffusivity of the particles is dependent on the solution temperature. At higher temperature, the diffusivity of the particle will be high, and that may lead to higher rate of agglomeration. The second one is orthokinetic agglomeration, where the particle transportation brought through fluid motion can cause an enormous increase in the rate of interparticle collision. An aggregation brought about in this way is known as orthokinetic collision. Such collisions occur under conditions of high shear rate, and either this can be either by steering or any kind of high shear flow. So this orthokinetic aggregation is dependent on the initial particle size and the velocity gradient, but it is independent of temperature. For instances, suppose steering doesn't enhance the aggregation rate of the smaller particle sizes until they grow and make the size of 1 micrometer. Once the particle reaches at that size, particularly, then the more steering will more promote the aggregation. But always remember that very high shearing may cause breakage of the agglomerates also. So we need to maintain the shear rate for the orthokinetic agglomeration, which is very important parameter. So we are going to discuss more about the perikinetic and the orthokinetic agglomeration. So here we can see that this is the initial particle position, which is referred to this, and the final particle position is referred to the dashed particle position, where the largest particle and a smaller particle different is mentioned in different colors. So they ultimately form the agglomerate, where it is the perikinetic agglomeration which is dominated by Brownian motion. Here the size of the agglomerates, that is dt, is linearly dependent on the time of agglomeration. So here you can see that it is dt to the power 3, it is a1 plus b1 into t, where the dimension for a1 is l cube or volume. That means and the B1 having dimension of t to the power minus 1 and t having dimension of t. So it is a um, uh, dimension is balanced in such a way. So here the agglomerate size, we can use this equation and we can calculate the agglomerate size for the perikinetic agglomeration. Whereas in the orthokinetic agglomeration, which is a shear dominated system, here the larger particles are there and the smaller particles are there in a flow condition or shear flow conditions, where they come closer to each other and col- uh, they coalesced particles and they form the agglomerate. So for that case we take the logarithm of the um, diameter or the agglomerate size at a time t to the agglomerate size at a time 0 is related to the a2 plus b2 into t, where a2 is dimensionless, and because this quantity will be dimensionless, so a2 is dimensionless, b2 is t to the power minus 1, so t is having dimension of t, so it will be dimensionless as a whole. So here itself agglomerate size at the time t is denoted by dt, so we can also calculate the agglomerate size using the orthokinetic agglomeration mechanism. So we are also want to define the characteristics time, that is half time, which is defined as the time at which the number of concentration of the particles become half of its initial value in a monodisperse system. So that is n t by t half is equals to n naught by 2, where k is the collision or agglomeration rate constant, which depends on whether we are following the mechanism for perikinetic or orthokinetic process. This characteristics time or the half time is the time scale of the agglomeration that tells us how quickly the suspension destabilizes due to the collision. So here the smaller the value of half life, the faster will be the agglomeration, the faster will be the destabilization of that suspension. And it also depends on the collision kernel K, which refers that higher collision frequency will reduce the um, half time or the characteristics time, and initial concentration, if it is more, then there will be more collision and there will be again reduction in the characteristics time. Whereas Walton arbitrarily they define that any kind of agglomerating system as will be there will be more than 10% of the original number of particles will be agglomerated with less than 1000 seconds. So they that is also you can say that it is a characteristics time defined in such a way that any kind of agglomerating system has that within 1000 seconds the 10% of the original number will be agglomerate and settle down. So this is the characteristics time that we define for both perikinetic and orthokinetic processes. So any kind of agglomerate where we need to know the factors for stability of the agglomerates. So, affecting the factors affecting the agglomerate stability, that is the particle surface chemistry. So, adjusting the pH of the solution or the mixture to isoelectric point can enhance the dispersion, and they may prevent the agglomeration by increasing the particle attraction. So, this pH or particle surface chemistry also plays important role because they also control the particle agglomeration depending on the surface chemistry. Particle concentration that already discussed, that high concentration lead will higher collision rate, which increase the breakup of the pre-formed agglomerates, and they stabilizing the system at a certain size. Hydrodynamic condition, when the fluid motion creates high shear stresses, they also can fracture existing agglomerate. Interparticle forces, van der Waals forces contribute to particle adhesion, and thus the stability also is influenced by the interparticle force, but also make the system prone to agglomerate if the interparticle force is very high. So these are the factors that may negatively or positively impact the agglomeration stability in the mixture. So these agglomerates which is formed perikinetically, can be unstable because they become larger and then susceptible to breakage from high shear force of the fluid if it is present, especially when it is the mixture is at higher agitation condition. The final agglomerate size will be limited by the balance between perikinetic collision and the shear induced breakage, this balanced condition. So during orthokinetic aggregation, particles can form agglomerate until they reach a certain size, at which the shear stress becomes high enough to break them apart if it is more. The orthokinetic process often leads to a stable equilibrium size. The rate of breakup of this larger and potentially more stable agglomerate will be dependent on the hydrodynamic condition or the shear stress condition. So we have discussed all about a basic introduction of the compaction of the granulation process and their mechanism. Now we are moving towards the pressure compaction or the dry granulation part. So as we have already discussed that the dry granulation is the process where we are not using any kind of binder liquid to form the granule. So it is only the mechanical pressure or compaction that we use to form the briquette or tablet out of the dry powder. So it is the process where granules are formed without any aid of any liquid solution. The process, if the ingredients to be granulated are very sensitive to heat or moisture, we use the process of dry granulation. Compaction is used to densify the powder and form the granule out of that. So this process is carried out using slugging tool or roller compactor or tablet press machines. Slugging is a process where the original method of dry granulation employed a heavy duty tablet press to compact the dry powder. The compaction process in this case known as slugging, and the compacted material therefore known as slugs. Typically they are 25 mm in diameter and 10 to 15 mm thick. A hammer mill will be ideal for that case, breaking up the slugs to create the granules of desired size. A manufacturing company may also use a conventional table machine or heavy duty rotary press for compacting the dry powder. Second one is we are going to discuss roller compactors, which is very similar mechanisms of roller crusher. Anyways, it is kind of gentler um, alternative to the slugging process, which is compaction using a roller presser or roller compactor. In this machine, the mixed powder is squeezed through two counter-rotating rollers to form a compressed sheet. The sheet is brittle and break easily into flakes. Now the flakes need carefully treatment to break them into granules, after which they are milled to desired size. Roller compaction or dry granulation equipments offer wide range of pressures, roll types to attain proper densification. This equipment is very loud and dusty compared to the other process machinery, and the material feed rates are very critical for attaining the final objective here. The process may require repetitive compaction steps to attain the proper granular size and the quality at the end. So this is the process where the two roller rotates in anti-clockwise to each other. Sorry, um, two rollers rotate in opposite to each other, and here you can see this is the feed material, the plastic feed material, and they form a sheet between the it forms a flat sheet, and that they produce the flakes, and flakes are again milled to form the granule. So here is the pressure displacement diagram, where the intermediate pressure region is this one, and the high pressure region is the at the line passing through to center of the rolls. Okay, so the next dry granulation process that we are going to discuss, that is the extrusion process. Extrusion process is nothing but also the similar process where the powder and binder, powder if it is dry and binder if it is wet condition, is forced through a die of desired cross section. This is the die of this cross section is desired, and we can set um, or screen under pressure and forming cylindrical strands. You can see this is the cylindrical strands they are producing out of the extruded plastic section emergent, and we are heating the process in the process of this extrusion. And commonly extruded material are metal, polymer, ceramic, concrete, and kind of foodstuffs. This extrusion process can be continuous or can be semi-continuous. Also, the process can be done in the cold compression, cold extrusion process, or it can be heat extrusion process. Suppose you are dealing with plastic powder or plastic powder, so we need to heat it to make it a cylindrical strand. So in that conditions, we are using the heating operation here. So this is the similar thing here. The die, this is the die, and this is the this diameter we can fix. This is the desired. So this is the extruded product or the cylindrical strands that we are producing out of the extrusion process. So in general, the dry granulars that are formed, dry granulation that forms granules without using any solution, because the materials will be that needs to be granulated may be sensitive or very sensitive to moisture or heat. And the method that is mechanical compression that force primary fine pores particles to come together to make a high dense agglomerate. Then the dry granulation process have fewer process stages than wet granulation. That is the only advantage. And particles are placed under very high pressure. Solid bridges are formed due to plastic deformation, brittle fracture, or local melting and or fusion. and mainly the solid bridges and the mechanical interlocking are the driving forces in this case. So we already have discussed the processes: extrusion, roll press, tablet press, molding press or pellet mill are the examples for pressure complexion method of size enlargement. And then we are going to discuss about the wet granulation process. So let's now discuss about the wet granulation process. So wet granulation process, that is the tumbling granulator. Tumbling granulator or coater includes a disc, drum or pan and a range of similar equipment. So in tumbling granulator, particles are set in motion by tumbling action caused by the balance between the gravity and the centrifugal force. These granulator have the following characteristics: that the product size of the granule should be in the range of 2 to 20 millimeter. Tumbling granulator are not suitable for producing very small granules. Now, these are very good for producing high density pellets. It is more difficult to produce high porosity agglomerate. Now, this tumbling and equipment can also be used for coating relatively larger particles, and the disc or drum granulator generally operate continuously and can be up to 4 meter in diameter. They are capable of very large throughput up to 100 tons per hour, and therefore they are extensively used in mineral processing and the fertilizer granulation process. So now we are going to discuss about this granulator. It consists of a tilted rotating disc with a rim to hold the tumbling granules. Powdered material are fed continuously into the disc and typically at the edge of the rotating granular bed. Now the liquid binder is added through a series of single fluid nozzles distributed across the face of the bed. A coating of the feed powder builds up on the disc to form a false base on which the mass can be rolled easily. The um, thickness of this um, layer can be controlled by any scraper or plows. The tumbling motion, that is defined as the smaller particle will stay in the middle and larger particle will roll outwards. So they cause segregation and size classification, which is central to the disk operation. This natural classification ensures only the granules of desired size are discharged, while the smaller ones will stay inside to keep growing and keep agglomerating further. The frictional forces between the granule and the disc hold smaller particles longer as they are carried up the disc, and the smaller particles will travel higher on the disc and they roll underneath the larger pellets in the eye of the disc. Thus, the larger well formed granules sit on the bed of new nuclei and granulated powder. This process leads to natural size classification on the disc, and only large granules or pellets overflowing the eye are collected as a product. As a result of this natural size classification, the disc granulator rarely need to recycle undersized and oversized granules, which is a distinct advantage over drum over drum granulator. The segregation of the granules on the disc also allow the balance of the granulation process to be controlled by adjusting the position of the powder feeder and liquid spray nozzles. So this is the diagram for the disc granulator. Here you can see the undersize is remaining at the middle of the smaller particles will be retained in the middle, and the larger particle will be coming at the outward of the disc. Now here what is happening, it is rotating and the recycling of the fine material will be inside the disc only, it will not come out. The concentrated solution will be continuously sprayed solution, and the smaller particles which retained into inside the disc, they are more allowed for the agglomeration process. So this is the inclined one where h is the height of the side wall and d is the diameter of the plate, where alpha is the inclination angle of that disc, and here you can see n is the number of rotation that you are rotating of this um, disk. So here the key operating parameter for the disk is the critical speed, which is defined by this formula, where it is beta. If it is beta, then it is like mg sine beta. At a critical speed condition, these two forces will be equal, and from that you are calculating the nc, which is critical speed. It is defined as the speed at which the granule is just held stationary on the rim of the disc by the centripetal forces alone. Now the discs are typically operated between 50 to 70% of the critical speed with an angle beta between 45 to 55 degree. If the speed is very low, the particle mass will slide against the disc inside the tumbling instead of tumbling, and if the speed is very high, then the particles are pinned to the rim or may be thrown off the disc. Optimum drum speed should be maintained for proper flow properties. The total holdup of the granules on the disc can be adjusted by varying operating parameters, which the holdup will increase with decreasing the disc angle at the same fraction of the critical speed. Also increasing the disc speed, granules are carried higher on the disc and cover larger fraction of the disc area, and increasing moisture content, granules are thicker, therefore they can carry higher on the disc. Typical granule residence time in this disc granulator is up to 1 to 2 minutes. Then the next category is the drum granulator. So these drum granulators are extensively used in the mineral processing and fertilizer industries. They are capable of large capacity. In contrast to the these granulators, there is no size classification at the output, and these drum granulators are often run with large recycles of undersized and crushed oversized granules. A granulation drum consists of an inclined cylinder which may be open ended or fitted with annular retaining rings. Fits may be either pre-moistened by mixture to form the granule nuclei, or liquid may be sprayed onto the tumbling bed via nozzles or distributed pipe system. Scrapers are often but not always used to limit the buildup on the drum wall. The desired granule motion in the drum granulator is a tumbling and cascading motion, just like ball mill. Drums are operated as a smaller fraction of critical speed than the disc. Typically, they are operating at 30 to 50% of the critical speed. If the drum speed is very slow, the granular bed will slide rather than cascade. High drum speed will give unwanted cataractic motion of the charge, and similar to that motion happens in case of ball milling. The drum pitch angle is simply to assist the flow of the charge through the drum. Typically, the drum pitch angle maintains 0 to 10 degree. Hold up in the drum is generally 10 to 20% of the drum volume, and the hold up and the mean residence time are controlled by the drum length, which is typically 2 to 10 times the drum diameter. This hold up in the drum is increased by reducing the pitch angle or providing a lip at the drum exit. Residence time is generally 2 to 5 minutes are common. So here we can see this is the drum, and it is inclined, it is placed as an inclination of 0 to 10 degree. 0 to 10 degree. Here the spray, continuous spray is happening. Solid is fed from this, solid is fed, and here we can see that granule bed are, this is the granule bed, and we are getting the exit, the product of the agglomerated product we are getting at the outlet. Here, these are the motions of drum granulator flow pattern. This is completely sliding. Here, no agglomeration is taking place. This one is the cascading, wherein one after another, this one is cascading, just like ball mill we have discussed lot about. And this one is onset of cataracting. Here, the with in the presence of the uh, spraying of the liquids. Next one we are going to discuss about mixer granulator. That is also a category of wet granulation. So mixer granulators use mechanical impeller to cause powder motion, while the granulator as a whole is usually fixed in space. Here also liquid binders are sprayed, or sometimes it is just poured into the granulator onto the moving powdered bed. Mixer granulators tends to make smaller, denser and less spherical granules than their tumbling counterparts. These mixer granulators are used in wide applications for pharmaceutical, clays, ceramic, detergent or agricultural chemicals. They handle wide range of feed materials than the tumbling or fluidized granulator, including very fine cohesive powders and very viscous liquid binders. This is due to the ability of the impeller or the chopper to break up the clumps of the material and mechanically disperse into the liquid binder more efficiently. However, the complex flow pattern and the wide range of the shear rate and simultaneous influence of all three rate processes make control of the product attributes in mixture granulation very difficult. The mixture granulators can be divided as high shear or low shear mixture. These are the advantage that mixture granulator can process cohesive powders and spread very viscous binder as well. They will generally produce a product which is more robust than the other process and only process to make smaller granulates that is less than 1 mm in size and more dense granules can be produced. But disadvantage it has high capital maintenance and operating cost. Granules are less spherical than the other processes and most complex of the granulator difficult to scale and maintain attributes. Where we are going to discuss about the high speed mixture granulator. Here the high shearing mixture. Here the impeller or the chopper rotate at moderate to very high speed, generating very high shear rate and impact velocities in some region of the mixture. So here we can see this is the horizontal shaft and this one is the vertical shaft. This one is the impellers and this one rotate like this and the binding liquid is spread and there is one chopper. Depending on the design and the flow patterns, the region may be only a small portion of the whole mixture. Batch type high shear mixture can be further divided into three categories. There can be vertical shaft, horizontal shaft or eccentric shaft. This one is horizontal shaft, this one is vertical shaft and eccentric center I will show you in the later slide. In this mixture, the impeller blade or plow rotate at a speed of 60 to 80 rpm depending on the scale and the design of the impeller tip speeds of order 10 meter per second. Most designs incorporate an off-center chopper which is rotating at a very high speed of 500 to 3500 rpm. These mixture granulators range in the scale of 10 liter to 1200 liter and typically their batch time are of order 5 minutes. The batch high shear mixture granulator are used extensively in the pharmaceutical industry where they are valued for their robustness and ease of enclosure. The next one is the Eric mixture granulator with eccentric shaft is a very unique design. Both the impeller blades and the chopper rotate eccentrically mounted over the vertical shaft and in addition the bowl rotates giving a hybrid effect of some features of the tumbling granulator. This type of granulator gives more spherical granules than those achieved in other batch high shear mixture. The Eric granulator is commonly used for granulation of ceramics and clays, although it is used in other industries is very limited. And continuous high shear mixture granulators, they are used for medium to high capacity processes. They are both horizontal or vertical shaft designs are available. Example, vertical um, sku- shugi mixture and horizontal pin or peg mixture. So this is one example of the peg granulator, where most of the design have the blades and pins mounted over the vertical shaft, which rotates at a very high speed. The action of the blades promotes powder mixing and the binder dispersion, as well as controlling hold up by the rate at which feed material is transported from the feed to the discharge end of the granulator. Typical residence time are in order of the minutes. Mixture operate at a high speed of 200 to 3500 rpm to produce granule size of zero point 0.5 to 1.5 mm. This is an example of the peg granulator, which is used for the ceramic glaze or making the carbon black particles. And then it comes low speed mixture granulator, that belongs pug mills or paddle mills. Both can be used for batch and continuous operation. So these devices have horizontal troughs in which central shaft with attached mixing blades rotate relatively slowly, rpm less than 100 rpm. So these mills have largely been replaced by the tumbling granulator in fertilizer or metallurgical applications. However, these are still used commonly in the pre-mixing step for blending very different raw materials like dry powder, wet filter cake. So here it is the twin rotor system, and this one is the single rotor pug mills. These, these are the slow speed mixture granulator. So we are now going to discuss about the fluidized granulator, that is the wet granulation part. So in this case, the fluidized bed granulator, where an airflow is introduced from the below of the powdered bed to lift the materials and agitate into the system. This fluidization process, they transform the dense powder into fluid-like state for more uniform and efficient processing. The liquid binding solution, which can be any kind of solvent or water, will be sprayed onto the fluidized powder to promote the granule formation, its growth, as particles will be stick together and they form the larger masses. You can see in the picture. Now the fluidized bed provide very good mixing and temperature control capability. So this feature will allow customization of the process parameters like airflow rate, spray rate, inlet air temperature, and humidity to produce the granules with desired properties. So, what are the stages that are associated in operation of fluidized bed granulator? So, we are going to discuss the stage of this process. First one is the free flowing powder that is being fed into the granulator from the overhead. So, powder is introduced into the system. Then an airflow is introduced from the bottom of the granulator to lift the particle up, and as the air velocity increases, a point will be reached where the drag forces will equal the particle weight, and that time the bed will be completely suspended and behaves like a fluid. The bed will be preheated to operating condition, temperature condition during this time. So once the bed is fluidized state and also reach the desired temperature, the liquid solution will be spread onto the fluidized particles through the nozzles. and this liquid contains binder and any kind of granulating agent. So as the droplet will contact the solid particles inside the granulator, the liquid spreads and binds particles into larger agglomerates. So here solid bridges form and other kind of interaction happens to make the agglomerates. As more liquid will be added over the period, larger irregular granules will start. At the proper liquid saturation, at a typical value, the nearly spherical and well-formed granules are achieved. So here the heated inlet air is introduced um, uh, and separate heating coils remove the moisture from the wet granule to make them more hardened, and cool down the phase brings the granules to suitable discharge temperature. So hot air in, hot air out, and other cooling method happens to make the product that is discharged at a suitable temperature to handle. Final granules are passed through the vibrating screen for, or maybe it may have to process through mills to achieve the size distribution of the desired product. And overseas material will be further recycled to the milling process. So, what are the parameters that may affect here? Liquid feed or spray rate. So, when it is increased, then that may also increase the size and the spread of the granule size distribution, and it will increase the granule density and strength, and there will be chance of defluidization due to quenching if the spray rate is very high. And liquid droplet size, if it is very bigger or increasing, then it will also increase the granule size distribution. If the gas velocity is increasing condition, then it will increase the attrition and elution rates, which are the major effects in the fluidization condition, and it may decrease the coalescence and that will affect the initial growth, and no effect on the coalescence for the non-internal growth, and there will be increase in the granule consolidation and density. Bed height, if it is increasing, then there will be increase in the granule density and strength. Bed temperature also, if it is increasing, then it will negatively impact the granule density and strength. Binder viscosity, if it is increasing binder viscosity, then it will increase the coalescence for the inertial growth, no effect on the coalescence for the non-internal growth, and decrease in the granular density. Then the particle or granule size, if it is increasing itself, then there will be decreased chance of the coalescence further, and increased required gas velocity to maintain the fluidization at that condition of bigger particle size. Next, we are going to discuss about the centrifugal granulator, which is also part of the wet granulation process. So here the equipment use the centrifugal force to convert the fine powders into uniform or spherical granules. Now, every time I say spherical granules, that is the ideal scenario that we can think of. Maybe in the real process, it doesn't follow the actual shape of the particle of granule in a spherical manner, but still it is effective enough to form the agglomerate in a size range, desired size range. So it is different. This centrifugal granulator works differently from the high shear mixture in that the granulation is achieved by the rotational force and controlled by the binder spring rather than intense mechanical shear. So this granule formation occurs under the combined effect here of centrifugal force, rolling and binder addition, where the fine particles will coalesce to round and dense granule formation. In each of these design, a horizontal disc will rotate at a very high speed, causing the feed to form a rotating rope at the wall of the vessel. There is usually an allowance for drying air to enter around the edge of the spinning disc. The centrifugal granulator tend to give more denser granules or powder layer than the fluidized bed, and more spherical granules than the mixture granulator. The advantage it has that it produces spherical and uniform granules with excellent flow conditions, flowability, lower mechanical stress compared to the higher shear mixture, and better for formulation of required control release due to smooth granule surface. Can handle also heat sensitive material, but disadvantage has it has lower granulation compared to the higher shear granulator, not suitable for very cohesive or very sticky powder kind of material, and it requires more precise control over the binder spraying to avoid overweighting in the process. And the last topic we are going to discuss for today's session, that is sintering, which is also a mean for process of size enlargement through the thermal medium. So what is happening here? We can see that sintering is a powder processing method in which the fine particles are heated, but they are not actually melted completely. They are just heated so that they bond together at their contact point, form the larger and stronger, more denser mass. It is widely used in the metallurgical, ceramic, pharmaceutical, or any kind of material science dealing department. Unlike pressure compaction, where we use extrusion, roll pressing, or tablet pressing, sintering relies mainly on the heat driven particle bonding rather than mechanical force. So, here finely divided particles are arranged in close contact with each other. The powder will be heated at a temperature below the melting point. At this point, the particles touch each other and they form the neck, and they are linked to each other, they form the neck. With time and temperature, they grow. The necks grow and reduce the porosity and increase the strength. So here it decrease the porosity, increase the necking, and increase the strength. The structure overall it will shrink and densifies over the period, and it also produces a very solid mass will reduce porosity. This agglomeration process through sintering has main driving force as reduction of the surface energy. So we can see that when the particles are not separated, are making that the smaller particles will have higher surface area. So higher surface area will have higher surface energy. But in the process of agglomeration through sintering, we are making the agglomerate, so it is having lower surface area, so surface energy is reduced in the process, and this is one the main driving force in the sintering process. So here the fine particles have high surface area and high energy. Heating allows the atoms to diffuse to minimize the surface energy, and thus they form the agglomerate. So in today's class, we have discussed about a important topic for the size enlargement. There are also very advanced topics for size enlargement, other compaction methods, and other um, weight granulation methods are also have been explored. We have not discussed those variety in today's class, but you can refer any recent literature for having the knowledge regarding the advanced technique for the weight granulation process. And for today's class, this is up to the lecture that I would like to present, and we have discussed a lot of things about the size enlargement process and equipments. So if there is any question regarding to this session, you can drop messages in the question and answer platform in the NPTEL online section. And in the next class, we are going to discuss about let me check. we are going to discuss about the flow past about black bodies. That will be very interesting and very engaging lecture in the next session. So I hope you will join for attending this live classes for clearing your doubt. So I would like to end the class here. Thank you. We will meet in the next session.